All right, welcome to week number 4. So the title of the lecture series is Probing Quantum Materials with Light, and this week we're finally going to get into how to probe things with light. So that's very exciting. This week is going to be more of a general overview, how the different types of scientific instruments work. And then next week it'll be back to more theory and math, like why do the different techniques work the way they do, with group theory and mathematical explanations of exactly what the selection rules are. And then we'll wrap up with a bunch of really concrete examples in the last lecture about probing quantum materials with light. All right. So what is optical spectroscopy? I've managed to make a career of it so far, but in general, it's just shining light on a sample and observing what the changes in the light are. And you do this to gain information about the sample. And the information can be encoded in a bunch of different ways. It can be encoded in the light's wavelength, the amplitude, the phase, the polarization, the timing, color the light is after it interacts with the sample, how much light there is after it interacts with the sample, what is the polarization after it interacts with the sample. All these things provide information about the crystal structure of the sample, the energy levels of the sample, and all these things happen sort of at once. And so understanding exactly what's going on in the instrument allows you to sort of start decoupling the different processes and understanding the data that's coming back so you can make good interpretation of the data. And it's not just a black box. You push the button, it spits out an answer, and you give the answer to your PI. And that's not the way to do science. You want to understand what's actually going on so you can correctly interpret the data that is coming back. But optical spectroscopy is really not that complicated and scary. I mean, you do it every time you go to the grocery store. You go to the grocery store, you shine white light on the bananas. Some of the bananas reflect back more green light. Some of the bananas reflect back more yellow light. But then optical spectroscopy is not the end all be all. I get students coming in and they want to just push the button and have the answer spit out. You need some extra information often about the sample. For choosing bananas, which bananas to buy, you need extra information about whether you want to eat the banana right now, so you want to get a yellower banana, or whether you want to have bananas for lunch later in the week, and so then you get some greener shade bananas. So there's lots of information encoded in the light after it interacts with the sample, and we're going to see different ways today of pulling out that information and trying to understand exactly what it's telling us. There's really only a couple different ways that light interacts with matter. So we can have light come in and just be reflected back off. You see this in the mirror every morning. The light just reflects back off the mirror. When you take a hot shower and there's little water droplets on the mirror, then your mirror is foggy, and so then the light ends up being scattered off the curved surface of the water droplets. The light can be just absorbed by the sample. So if you have something that's colored and you hold it up to white light, only certain colors get through, other colors are absorbed by the sample. So here, if this was a piece of green glass, the blue light ends up being absorbed by the green glass. The light could be absorbed and re-emitted. So if this was a fluorescent sample, you can send in blue light and you can have yellow light being re-emitted, and some energy is lost into the sample. We can have light just be transmitted, and we can go from lots of photons to a few photons on the other side if we wanted to measure how much light is transmitted. Or the light could change the polarization as it went through the sample. We talked a little bit about birefringence the other week. And it could also change the phase, which will change the interference patterns on the other side. At the heart of most of the optical spectroscopy tools is a diffraction grating. So we've talked a fair amount about diffraction so far. The two slit experiments that we've talked about are diffraction experiments. Instead of just two slits, we have hundreds or thousands of slits. And instead of slits, they're actually grooves in this particular example that I have a picture of. You can set up diffraction gratings so that they are slits. You can also set them up so that it's grooves, but it effectively acts as the same thing. And then the blaze is the number of grooves per millimeter. So a higher blaze grating will spread light out more. And then as you can see, if we shine white light onto a diffraction grating, we get constructive and destructive interference at different angles, and this spreads out the light like a rainbow. So you can see the light goes from blue to red in this picture. And this is really crucial to making our measurements of different wavelengths of light, because it's transferring the information of what wavelength it is to a spatial distribution of the wavelengths. And then we can take a picture of the spatial distribution with a digital camera, just like I did here. And that digital camera, we can record that this is the intensity at the top, which we know corresponds to the blue region. This is the intensity at the bottom, which we know corresponds to the red region. And now we can quantify how much light, how many photons there are of each color as we go across the digital camera. So sometimes we want to sort photons and send just one color of photon into our sample to interact. So this is often done with what's called a monochromator. Monochromator means one color. So we can start with a white light source, a xenon lamp, tungsten filament, light bulb, some sort of white light source. We send it, we usually focus it and collimate the beam and send it through an entrance slit. The light will then spread out after it's been focused through the entrance slit. It goes off an imaging mirror. So in monochromators and spectrometers, we usually use all reflective optics, and that gets away from what's called chromatic aberration. The different wavelengths will travel at different speeds through refractive optics, through glass, through lenses. And so going to all reflective optics gets us away from that particular issue. So we go off an imaging mirror, the mirror is curved, which then focuses the light back onto the diffraction grating. The diffraction grating spreads out the light like a rainbow at each of these points. And then the focusing mirror, again, a curved parabolic mirror, focuses the light back down. And at the focal point, we put an exit slit. So here we can put an exit slit and just let the green light out. If we wanted to change which color light is coming out, we can rotate the diffraction grating. As we rotate the diffraction grating, the red light will make it out of the exit slit. If we rotate it the other way, the purple light can make it out of the exit slit. So now we've gone from a white light source to a single colored source, and it's tunable. We can switch back and forth between different wavelengths. So that's a really useful key feature in some of these spectroscopic techniques, spectroscopic instruments. The other thing we can do is, this particular geometry is called the Zerny-Turner spectrometer. I joke that my job is about taking pictures of rainbows. You'll see this looks very similar to the monochromator. We again have an entrance slit. We're sending it, focusing in whatever our signal is. It goes off the imaging mirror, off the diffraction grating, which just spreads it out. And then instead of an exit slit, we put an array detector. So typically today, this is just a digital camera. Each of these little squares is 1 pixel on the digital camera. And we have it calibrated so that we know if the light hits this pixel, it's purple. If the light hits this pixel, it's green. If the light hits this pixel, it's red. And then we can count how many photons hit each of those pixels and quantify how much of each color of light we have. So my job is to zap things with lasers and take pictures of rainbows. Here's how I take pictures of rainbows. So we've talked a little bit about how weird and quantum mechanical photons are. They have momentum but no mass. They're waves, they're particles, yeah. So we actually have no idea how to count photons. They're so weird. What we actually count in the detectors are electrons. So all the detectors work, and basically we have, in your digital camera, it's always a semiconductor chip. There are photomultiplier tubes, which are sort of fading out of use, but they work by the photoelectric effect. Here, your digital camera works by having a bandgap. We talked about bandgaps in the first lecture. We have our valence bands where the electrons are bound to a nuclear core. And we have the conduction band where the electrons are free to move around. We can bring in our photon onto this particular pixel. It will excite the electron from the valence band up to the conduction band, assuming that the photon has enough energy to excite the electron across the bandgap. So this is why different detectors are important for different wavelength ranges. So silicon has a bandgap of 1.1 electron volts, which is about 1,100 nanometers. So if you want to detect a photon that's 1,550 nanometers, which is what's commonly used in fiber optics for telecommunication, you can't use a silicon detector. It's just not, it doesn't have the right energies. It doesn't, the photons won't have enough energy to get the electron over the bandgap, and you won't detect anything. Here, we'll pretend this is silicon. We bring in a blue photon, we excite the electron, and then the electron can be whisked off to some electron counting circuitry. And as we have gotten very good at microelectronics, we're very good at counting electrons. The electrons can be excited with a photon. They can also be thermally excited sometimes. So this is why you cool your detector, and that's to minimize the thermally excited electrons. We only care about the photo-excited electrons. The thermally excited electrons are just background baseline offset noise that wipes out your signal. So you can cool detectors with liquid nitrogen. That's becoming less common as thermoelectric coolers have gotten pretty good. So you can have a thermoelectric cooler, which is a special type of material where you run electricity through it, and one side will get cold and the other side will get hot. And you can get them to cool down your detector to about -70 Celsius quite reliably. So that's what most modern detectors are going towards. All right, and why? Oh, there goes the electron into the electron counting circuitry. The other thing to be aware of when we talk about optical spectroscopy is resolution, especially when we get into nanomaterials and things like that. You can only focus light to a certain size. It's called the diffraction limit. In round terms, it's about half the wavelength of light. There's the specific formula, it's 1.22 lambda, where lambda is the wavelength of light over the numerical aperture of the condenser plus the numerical aperture of the objective. If you're using a transmission microscope, if you're using a reflective geometry, then the condenser and objective effectively are the same because you're using the same lens as the condenser and the same lens as the objective. In round terms, just remember lambda over 2. So if we have 500 nanometer light, which is sort of blue-green color, the smallest particle we can resolve is 250 nanometers. And so what do we mean by resolve? So it's being able to tell two particles that are next to each other if there's one particle or if there's two particles. So in this picture, there are some particles that are right at the resolution limit where they're right next to each other and you can just tell that there's two of them. Some are fully resolved, that you can tell that they're spatially separated, and some are unresolved, that are too close. You can't tell if there's one particle there or two particles there. when you focus light really tightly, you usually get these diffraction rings, the airy disks. They're not important for today, but just know that there's a limit to how small you can focus light. If you want to resolve things that are smaller, then you can go to electron microscopy. But there's a difference between the resolution limit and the detection limit. So there can be objects smaller than the resolution limit, but you can still detect them. So if you bring a quantum dot and the quantum dot is 10 nanometers across, I can't resolve that the quantum dot is 10 nanometers across. It will blur out to a 300 nanometer spot when I look at it in the microscope. But I can tell you, I can detect it. I can tell you, yes, there's a quantum dot there. Similarly with carbon nanotubes or things like that, you know, you can't resolve them, but you can detect that they're there. The important thing to take away is that I can detect if there's a quantum dot there, but I can't tell you if there's one quantum dot or two quantum dots. I can just say, there are quantum dots here. If you make a dilute enough sample, you spread out the quantum dots far enough, then I can say one is here, one is there, one's over there. But that requires you to know that there's no aggregation, they're not clumping together. All right, so that was sort of the broader overview, and now we're going to dig into some of the specific techniques that probe the electronic energy levels. So we've been talking about electronic energy levels and band gaps and where they arise from. One way to probe the band gaps is to use absorption spectroscopy with UV-VIS-NIR. So we could start in a couple of different geometries. We could start with a white light lamp, go through our monochromator. So we have our diffraction grating, it spreads out the light like a rainbow. We let one color go in. We could have it reflect off the sample and go to a detector. And the detector would count the number of photons that hit it. And then we could have translate or rotate the diffraction grating. As we rotate the diffraction grating, we'll get different colors. And we can record as a function of diffraction grating position, how much light of each wavelength is reflected off the sample. We can do it in transmission geometries. So again, the white light goes off the diffraction grating through a monochromator. We just send the light straight through the sample. As we translate the rainbow back and forth, we'll get different colors going through the sample, and we can measure with the detector what wavelengths transmit best. We could also do it in sort of reverse. We could start with just white light and send the white light, all the colors at once, through the sample. And then we could do the photon sorting on the other side, run it through a spectrometer on the other side, and have the diffraction grating spread out the light like a rainbow and see which colors actually make it through the sample and which colors are strongly absorbed by the sample. So there's a couple different geometries where you can do it, or if you're trying to build something yourself, there's a couple different ways you can think about it. But what is that actually telling us? So this is an absorption measurement. So what color of photons are being absorbed? So photons have no mass, so we can create and destroy them as we want. But we still need to do conservation of energy. And we need to account for all the energy. All the energy from the photon must go into the sample. The sample can't make change for you. It's got to all be accounted for. So I drew a picture of two electronic energy levels, the ground state and the excited state. And within the ground state and the excited state are multiple vibrational energy levels. So we'll talk first about electronic energy level spectroscopy techniques, and then we'll talk about vibrational energy level spectroscopy techniques later today. But that's what the picture is supposed to represent. If we bring in a photon, and it has a certain amount of energy, but the energy doesn't correspond to any of these transitions. Here, the energy is too high to transition just between some vibrational energy levels, but not high enough to transition between electronic energy levels. The photon just goes right through the sample. The sample is transparent to photons of that wavelength. And that's because the sample can't absorb that quanta of energy that the photon contains. If we came in with a lower energy photon, now it does match a transition between two energy levels. And then it would move the molecule or sample into an excited vibrational energy level. So this is basically Fourier transform infrared spectroscopy, which we'll cover towards the end of the talk. We let the system go back to the ground state. We bring in a blue photon. Now the blue photon has enough energy to excite from one electronic energy level to a different electronic energy level. There are some key points about this cartoon. So you'll notice that the transition was purely vertical, and we went from the lowest energy level in the ground state to the third energy level in the excited state. So typically, light interacts with the electrons because they are so much, they have so much less mass than the nuclei of the samples. And so the vibrational energy levels have to do with the nuclear motion of the sample. And it's too massive and it's too slow to couple in a lot of the time. So it does occasionally. Occasionally you get phonon electron coupling, but it's a much rare occurrence. Most of the time you just get this pure vertical transitions. You don't have to couple into a phonon. If we stop and quickly review the particle in the box, then we'll also get into a little bit more of why certain transitions are allowed and why certain transitions are not. So if we solve Schrodinger's equation for a particle in a box, which is a very famous example, we have this box where we have infinite potential on the two sides, so the particle is never allowed on the two sides. And then the potential is zero within. We end up with quantized energy levels, and they go as sine and cosine. So we get these quantized energy levels, and the wave function, is the eigenvalue, and we went over eigenvalues last week. So the eigenvalues, the solutions that are allowed, end up being these sines and cosines, and these curves are the probability function of where you'll find the particle. So in the lowest energy state, you'll find the particle mostly in the middle. In the second energy state, you'll find the particle mostly on these two sides, and you'll never find it in the middle. So it's sort of funny that it's suddenly forbidden to be in the middle, but this is how it works out. All right. So in this molecular picture, these different vibrational levels all have their own associated wave functions. And you can think of it as two particles in the boxes offset from each other. And so I gave up trying to draw things myself and borrowed an image from Wikipedia. So here we have the wave functions with the different energy levels. And if we look, the wave function need to have overlap. We need to go from an area where the particle is allowed to be to another area where the particle is allowed to be. If we go from V0 in the ground state to, if we tried to go to V1 in the excited state, it's got a fairly low overlap. The particle's only barely allowed to be there. These wave functions leak out of the energy manifold because the potential is not infinite, so therefore you get sort of exponential decays going down the sides. But it has a much better overlap with this second energy level. So you're much more likely to get a transition going from V0 to V2. And then it will relax down, getting rid of some energy due to phonons, due to molecular vibrations. And then again, you have a vertical transition, and you're much more likely to go from V prime equals 0 to V double prime equals 2. Again, because you have this good overlap between the wave functions. And this wave function is the spatial probability. You need the spatial probability to be allowed. You need the particle to be allowed to be in both of the states, your starting state and your final state. So this is called the Frank-Condon principle, and it's why you get different energy levels, transitions that are more probable or less probable. So if we look at the absorption, for this example, we get a much higher probability of the 0 to 2 transition rather than the 0 to 1 or 0 to 3. And these probabilities are just based on the overlap between the wave functions. How much do the two wave functions overlap? So we've talked about absorption, the electron absorbing the energy from a photon and transitioning up. Fluorescence is sort of the opposite. It's the transition back downwards from the excited state to the ground state. And then we need to create a photon to carry off the extra energy. And as we saw in the cartoon previously, the most probable transition was the 0 to 2 in the fluorescence also. So in my lab, most of what is done for quantum materials in terms of absorption measurements are to determine the bandgap of the material. So when the light is below the bandgap, then the sample is pretty much transparent. And then once we hit the bandgap, it starts absorbing light very strongly. And so we'll start to get this slope going upward. This is what's called a talc plot, after the guy who first made it. And then if you fit a line tangent to this slope and project it back to the 0, that's what's usually interpreted as the optical bandgap. For this particular film, it was titanium dioxide. The optical bandgap was 342 nanometers, or 3.63 electron volts. So we talked about the bandgaps, and different materials have different bandgaps. And then you can engineer the bandgap or by doping it, putting in defects to the crystal structure on purpose, and that will tune the bandgap back and forth. And so measuring the absorbance where you get this turn on of strong absorbance on the sample will give you, did you actually tune the bandgap, or did your doping not work the way you expected it to? So this is a fairly powerful, straightforward measurement of measuring the optical bandgap of a material. And you can do this through a microscope. I have this set up on a microscope system also. And so then you can measure the bandgap of a 2D flake of material if you wanted, and you can work on doping the 2D materials. A sort of interesting example of this bandgap and how materials interact differently with light above and below the bandgap. So typically we think of silicon as this black material that's opaque because our eyes work in the visible region. And in the visible region, all the photons are above the bandgap. So the silicon ends up acting like a metal when it's exposed to visible light, just because so many electrons are excited above the bandgap into the conduction band. When you're below the bandgap, silicon becomes transparent. So if you're working in the mid-infrared range, you actually make lenses out of silicon. So these are some pictures of silicon lenses for thermal imaging, which is in the mid-infrared range. And it's one of those counterintuitive things. We work in the visible range, so we think of material properties in the visible range, but it's not the same across the whole electromagnetic spectrum. And a material that we're familiar with, silicon, ends up being an excellent lens if you're working in the mid-infrared range. All right, so I've mentioned fluorescence already. Fluorescence and photoluminescence are the same phenomenon. The chemists discovered it and called it fluorescence and then told the biologist about it. So if you're talking to a chemist or a biologist, they'll call it fluorescence usually. The material scientists and physicists discovered the same phenomenon and don't talk to chemists and biologists apparently, so they called it photoluminescence. But it's the same thing. You shine light on a sample, it absorbs the light, it re-emits light of a different color. So what color does the sample glow? Here I have a picture of some fluorescent dye, just with some blue laser light coming in, and we get a nice green fluorescence coming out. To measure the photoluminescence or fluorescence, we could again do it with our monochromator. We could send white light in, spread it out, send a single color in, and then measure what colors are emitted. We could put our monochromator on the front, we could put a spectrometer on the back if we wanted to sort photons more carefully on the back and have better spectral resolution. But it's again just shining light at the sample and seeing what color of light is re-emitted. So let's try to go down to sort of the molecular level again. So we again have our photon coming in. Here we're going to assume it has enough energy to excite up to an electronic state. It's going to relax through non-radiative relaxation. Non-radiative relaxation means it doesn't give off any photons. If it's radiative, it gives off photons. If it's non-radiative, it's dumping energy, but it's dumping energy usually into vibrational motion. You can think of it as heat of the sample. We think of vibrational motion of a sample also as heat sometimes. That's coupling into phonons, and you can see it translates along the x-axis in this diagram as we couple into phonons. And then it will eventually drop back down. So the system doesn't want to stay in the excited state forever. All things tend to the lowest energy state given enough time. And so we can let it relax back down. It can't stay anywhere in the bandgap, so it's got to dump all the energy across the bandgap out as a new photon. So it makes a new photon with the exact amount of energy between those two energy levels. So we put in a blue photon, here we're getting a green photon out. And then usually it relaxes a little bit more through a little bit more non-radiative relaxation. So this is why the absorption spectra and the emission spectra may not match up perfectly. It depends how many non-radiative relaxation levels are available in your sample. So you can measure the bandgap on the absorption side, and you can measure the bandgap on the emission side, and they may not give you exactly the same number, but that's understandable when you look at the cartoon. One is the upward transition, one is the downward transition, and it's the wave function overlap between the levels that it's transitioning between that will give you the energy of the photon that's going in and the energy of the photon that's coming out. So this is a project that came through my lab a couple of years ago. Max Menken was growing these nanowires of different sorts and getting them to grow on certain facets of the silicon nanowires. He was getting some cadmium sulfide growing on certain facets. And here you can see them glowing green. We were shining purple light, 405 nanometer light on it, and then it was glowing strongly green. And then there's a tiny little defect peak down here that you can't see very well on this plot. Out of this project with Max, we had to build our own spectrometer setup. And Max was, I think, a second-year grad student at that point, and he's had been sort of told, here, there's a whole room full of optics equipment and in his PI's lab, but everyone who knew how to do optics had graduated. So he was feeling overwhelmed and finally stumbled onto me. And I'm like, oh, well, this is what you do. You boop, boop, boop. And we built it in an afternoon or something like that. So Max decided we should write a book. So I wrote a book with Max on how to build optical spectroscopy setups to do characterizations and things like that. It's aimed for sort of first-year grad students, advanced undergraduates, and it's supposed to walk you through very basics of how to get around the optics lab, what's going on. So another thing we can do is we don't have to worry about just what color light is coming out, but we can see how long it takes to glow. So this is an example of, it's a reference sample of convallaria, which is some roots of a plant. The colors here are not what color is coming out, but how long it took to come out. So red is 555 picoseconds and blue is 2.1 nanoseconds. So how long it takes to fluoresce or photoluminesce can be highly dependent on the viscosity or the pH if you're in a biological sample, or the strain or the defects. In a solid state sample, you can have recombination centers, which would be defects where you give emission very quickly, the hole and the electron recombine very quickly. Or you can have trap states where the hole and the electron get trapped and they almost never recombine or take a long, long time to recombine. So we talked about the crystal structures back in the first lecture in defects. And you can get grain boundary defects where you have two crystals that are come together and they don't match up perfectly. And those defects can either lead to really short lifetimes or really long lifetimes. If you're trying to make an electronic device, if you are trying to make a high-speed transistor, you want really short lifetimes. If you're trying to make a photovoltaic, you want really long lifetimes. So understanding how long it takes for the electron and the hole to recombine can be quite useful and quite powerful. So how do we do that? We go back to our picture. We send in a pulse of laser light now. Instead of just steady state laser, the light's always on, we send in a pulse of light. And we set up our equipment so that we know when the pulse of light starts. And we start a little stopwatch. So the excitation light comes in, we start the stopwatch. The electron is excited, it relaxes back down. And then the question is, how long does it hang out here before it drops back to the ground state? And for different applications, you want it to hang out there for a long time or a really short time, it depends. But then when we detect the emission photon, we stop the stopwatch. And then we repeat this multiple times. And we eventually build up a trace like this. So each of these blue dots is one measurement. So even though this is the same sample, not every electron relaxes back down at the exact same rate. We end up having this exponential curve. It's all probabilistic, it's not deterministic. The probability that it will relax back down is a certain rate. In this example, on average, they're going to relax back down with a 2 nanosecond lifetime. But not every electron relaxes back down with the exact same lifetime. So one limitation of the time-resolved photoluminescence is how fast we can make the stopwatch go and the electronics. When we're dealing with electronics, at some level you have to move an electron across a physical space. It has to travel through the cable. There is a finite rate on which you can do that. It takes time for a signal to propagate through a cable. And so as you're trying to push this time-resolved photoluminescence, you end up very carefully measuring cable lengths and making sure the cables match and moving your computer very close to the detector so you can use a shorter cable and things like that. But there's a fundamental limit, and it's about 500 picoseconds in round terms. It's hard to get electronics to work much faster than that. So if you're interested in physical phenomena that occur faster than that, you need to move to a technique called pump probe spectroscopy. So the idea in pump probe spectroscopy is we again have our sample with our bandgap. So we have a bunch of electrons in the valence state. We bring in a pump laser pulse, and the pump laser pulse excites all the electrons to the excited state. Then we wait some time for the system to relax, and we're going to vary this wait time. So the system, some of the electrons eventually relax back down, and then we send in a probe pulse. So in this cartoon, all the pump pulse photons were absorbed, but because most of the electrons were still in the excited state, there were no electrons to absorb a lot of the probe pulse photons. So the probe pulse photons came through. This is a picture of transient absorption. But because there were fewer electrons available, we have a change in the probe pulse number of photons. So we can detect the number of photons that made it through in the probe pulse and understand the time evolution from the excited state back down to the ground state. So after the probe pulse goes through and we make one measurement, we wait for the system to completely relax. And then we're assuming the system has gone all the way back to the ground state, and we take another measurement and we vary the time delay between the pump and the probe laser, and we build up a histogram, at negative times, that's when the probe is actually before the pump. And then at time zeros, then the pump and the probe arrive at exactly the same time. And then at positive times, the probe arrives at different times later and later and later. And eventually it will recover back to a level where it was the same as if the probe went before the pump. So this is just the system by itself. So we can plot the change in the probe pulse versus the time delay, and we can monitor a number of different changes in the probe pulse depending exactly what we're trying to do. But this gets us down to the resolution of how long are our laser pulses. So in a titanium sapphire laser, it's fairly easy to get 100 femtosecond pulses. If you push everything, the absolute limit for a sapphire laser is 5 femtosecond pulses. You can move to soft X-rays, which are called attosecond pulses, and there's ways to generate those on a tabletop now. And then your time resolution would be attoseconds. But your limitation now is how long the actual pulse is, and it's nothing to do with the cables. You're not trying to translate an electron which has a mass across a length of cable, and how fast can you do that? You're limited. It can never go faster than the speed of light. So, but you can set this up to do transient absorption measurements, or if your system is not transparent, you can do transient reflection measurements, and you can do time resolved second harmonic generation measurements. I'll talk about second harmonic generation next. But this allows you to do really fast measurements. 100 femtoseconds is faster than the nuclei will respond. So this is a pure electronic response to the system without this convolution in with the nuclear motion of the system. So to control the time delay between the pump and the probe, when I first, I built a pump probe system for my senior thesis as an undergraduate, and when I first heard it, I was like, we're going to need all sorts of fancy stuff to control the timing between the two pulses, and it's actually remarkably simple. It's a very clever trick. You take your laser beam and you split it with a beam splitter, and now you have two pulses, and you send one pulse, your probe pulse, on a slightly longer path length, and then you recombine it with the beam path of your pump pulse. So here in this diagram, the pump pulse is going straight through the sample to the detector. The probe pulse is taking this longer route. And since the speed of light is fixed, we can control the arrival time of the probe pulse relative to the pump pulse by just translating the stage back and forth. So we just make the probe pulse run around a little further, and that will delay when it arrives at the sample relative to the pump pulse. And so that allows you to do very high temporal spectroscopy. So second harmonic generation is a type of nonlinear optical spectroscopy. So we said the photon has to have enough energy to go bring the electron from the ground state to the excited state. And if it doesn't have enough energy, then nothing will happen. There are cases where if you have two photons and they arrive at exactly the same time, then the two photons could couple both into the electron and still excite the system. This is a really rare phenomenon. But if you take all your photons and you squish them in time, so the femtosecond pulse, you squish a bunch of photons, like 10 to the 20th photons into 100 femtosecond pulse. So you have many, many photons in time, and then you focus it tightly with a microscope. So you have many, many photons in space. So you squish all these photons in time and space. Then the probability of this happening suddenly becomes finite, and it actually occurs. You get two photons coupling into the system, and that they can jump across the bandgap by absorbing two photons simultaneously. It's just the challenge is getting the two photons simultaneous. They need to be there in time and space at the same time. And then in second harmonic generation, we'll go through selection rules and the deeper math next week. I just want to get everyone sort of up to speed with the bigger picture of the different techniques this week. In second harmonic generation, we send in these two photons, and they're focused in time and space. And then the electron transitions right back down the way it came and puts out one photon at twice the energy of the input photon. So we put in two 800 nanometer photons, we get back one 400 nanometer photon. So our conservation of energy still works. We put in and got out. We put in a certain amount of energy, we got out exactly the same amount of energy. We just moved it from packaged in two photons to packaged in one photon. So the advantage of that is that the selection rules for second harmonic generation, they are forbidden in, it's forbidden in centrosymmetric media. So a centrosymmetric media is if you look up and look down and it all looks exactly the same. So imagine you're an atom sitting in the media. If you look up and you look down and everything's exactly the same, then that's a centrosymmetric media. It has a center of inversion symmetry. In non-centrosymmetric media, you get second harmonic. In centrosymmetric media, you don't. So that means in bilayers of TMDs, transition metal dichalogenides, the SHG is forbidden, but in monolayers or odd number of layers, it's allowed. So people want to use it as one measure of, do I have a monolayer or a bilayer? Because those can get very hard to distinguish in certain cases. And also they want to use the polarized second harmonic generation. So we talked about polarization is the direction of the electric field of light. So it has, if you have linearly polarized light, it has a certain direction in the laboratory frame of reference. And then we talked about crystal structure, crystal orientation in the first lecture. So the electric field has a certain orientation, the crystal structure has a certain orientation. If we rotate the crystal structure relative to the electric field, we can get variation in the second harmonic generation intensity. These images did not come out very well on the PowerPoint, but you'll have to trust me that there's different intensities as we rotate this TMD flake. And then we can measure the intensities off these grayscale images and plot that. If we pull something from the literature, here is two stacked molybdenum disulfide crystals. They're doing second harmonic generation. Here they're plotting in a polar plot the intensity of the second harmonic generation as a function of crystal angle. So flake 1, you get these certain lobes corresponding to the crystal orientation. Flake 2, which is rotated relative to flake 1, you get these crystal orientations. MOS2 tends to grow in these nice triangles, so it tends to be less imperative to do this second harmonic for MOS2 specifically. But other TMDs don't have this nice crystal facets, crystal faces when they form. And so if you're going to stack your crystals at certain twist angles, and they don't have a clear crystal orientation just by the shape of the flake, doing polarized second harmonic generation and plotting the intensity as a function of angle lets you figure out what the crystal orientation is, and then you can move to stacking them with certain twist angles. All right. So I'm going to stop there on talking about electronic energy levels, and now we're going to move to vibrational energy levels. So vibrational spectroscopy techniques, and there's two of them, Fourier transform infrared spectroscopy and Raman spectroscopy. They really probe the chemical bonds. So we have our little Bohr model of an atom. We bring in some other we bring in some other atoms, they form bonds. This is supposed to be water, a spectroscopist's favorite example molecule. Already I'm shortcutting, I can't draw enough electrons to make all this work. So I'm gonna be a physicist and shift to a ball and spring model, which actually works reasonably well. So instead of trying to draw all the electrons, we're gonna draw balls and springs. The white balls are the hydrogen, the blue ball is oxygen, there's your water molecule. And then physicists only have a couple tricks. One of them is the simple harmonic oscillator approximation. So the simple harmonic oscillator, we start with Hooke's law, which was written out in 1660, F equals minus kx. We take Newton's second law of motion, which was written out in 1686, F equals ma, but we can rewrite acceleration as the second derivative of position with respect to time. We can combine those two, minus kx equals m, second derivative of x with respect to time. We can plug in the time-dependent solution, and then we discover that omega, which is the frequency of oscillation of those of your balls and springs, is dependent on the square root of k over mu. K is the spring constant, and balls and springs, it's how stiff your spring is. And molecules, it's how strong your bond is. And then mu is this reduced mass. It's m1 times m2 over m1 plus m2. You just need to correct for exactly what the mass you're using is for the mass of the system rather than the mass of the individual ball. All right, so if we can just measure the frequency at which they vibrate, we can work out what the mass is and what the bond is and on some level. So here's our picture of balls and springs. So we're gonna, for water, there's specific modes. It can't wiggle, well, for any molecule, there's specific modes. It can't wiggle any way it wants. There's certain ways that it's allowed to move. So these are called the normal modes. A nonlinear molecule with n atoms has 3n minus 6 independent modes of vibration. You lose 6 degrees of freedom because the 3 degrees of translation and 3 degrees of rotation, and those don't change anything about the system. So we throw away the translation and the rotation, and then we have 3n minus 6 modes of vibration. Water has 3 normal modes because 3 times 3 is 9, minus 6 is 3. And they're referred to as the symmetric stretch mode, the asymmetric stretch mode, and the bending mode. And next week, we're going to really get into the group theory that is the formal mathematical structure and how to describe these and to determine if a molecule is IR active or Raman active or second harmonic generation active or things like that. So we'll get into group theory next week. But basically, the 3 modes are here with the oxygen sitting in the middle and the 2 hydrogens going symmetrically away from each other. The asymmetric, the oxygens are out of sync relative to each other. And then the bending, they're rotating around the oxygen. So those are the modes that are active in water. So we can do the quantum mechanical simple harmonic oscillator, and we find that the vibrational energy levels are also quantized, which we've talked about a bit. So Raman spectroscopy is probably the more heavily used vibrational spectroscopy technique on quantum materials. So it was discovered by Sir C.V. Raman. There's some debate. The Russians claim that 2 of their scientists discovered it a couple of weeks before Raman, but and apparently in Russian, it's still inelastic light scattering, however you say that in Russian, and not Raman scattering. Raman published in English and the Russians published in German, and somehow the English stuck rather than the German publication. Anyway, so it was this inelastic light scattering in an inelastic process, an inelastic collision, you lose some energy during the collision. If we had a bouncy ball and it's perfectly elastic, we drop it, it goes down, it comes back to exactly the level we started at. If we drop a bouncy ball and it comes back to a lower level, that was an inelastic collision, we lost some energy during the collision. So Raman discovered this inelastic collision of light by sending light through carbon tetrachloride. He was working in Bangalore, India, using sunlight. This is, I find, an astounding experiment because I've tried to take good spectra of carbon tetrachloride. It's one of the examples in a class I help teach. And doing it in the 21st century with modern equipment and lasers is challenging enough. The fact that he got this beautiful spectra in 1928 is amazing. He only had sunlight. Lasers weren't even invented until 1960. So Raman spectroscopy never took off until the laser became really common, sort of starting in the early 70s. But here we have a visible photon. It comes into our sample, and it doesn't have enough energy to excite the system to an electronic state, an excited electronic state. It goes up to what's called a virtual state, and there's an infinite array of virtual states within the bandgap. But because it's not a real state, it can't stay there. And it goes up. Most of the time, it just comes back down to the ground vibrational state, and what we see is Rayleigh scattering. That we put in a green photon, we get a green photon back out. Occasionally, we get a yellow photon back out, for instance. And there, it's started in a ground vibrational state, went up, but it's come back down to an excited vibrational state. And the excited vibrational state is different in energy. So then the color of the photon that comes out has to be different, because conservation of energy, we need to account for all the energy. The sample is taking up some of that energy, the difference between the ground state and the vibrational state. So then the photon that comes out has to be a different color. So we're going to measure that different color. here are these different lines correspond to the different colors of light that are coming out of his sample. If we go back to sort of the bouncy ball analogy, if we drop the bouncy ball, it bounces up to a certain energy level, and we keep track of the difference between where we initially started and where it comes back to. And we drop it on a hardwood floor, it'll come back to a certain level. If we drop it on a carpet, it'll come back to a much lower level. And when we plot Raman spectra, we plot it as the energy lost. So here there's one peak because all the hardwood floor samples, it bounced up to this level. Here there's another peak because all the carpet samples, it bounced up to a different level. So it's this energy lost relative to wherever we started. So we have our laser line. We start with a very narrow laser line for Raman spectroscopy. So all the photons have exactly the same energy going in. And then we see how much energy was lost relative to that input. So especially for quantum materials, we're usually doing micro Raman, sending things through a microscope. So we start with our excitation laser, which has a very narrow excitation line. Every photon is as identical as possible. And then we send it off a dichroic filter, and that directs the laser down through a microscope objective where it's focused onto our sample. So Raman is a really inefficient process. We throw in 10 to the 8th excitation photons, we get 1 Raman scattered photon back. We win by brute force. We throw in 10 to the 20th excitation photons, and then we get 100 Raman scattered photons back, and we're happy because that's out of the noise. But it's a really inefficient physical process. So we need to tightly focus our sample. Again, we're trying to squish photons in space to get better signal. We have the light come back, usually on a microscope. You're in this backscattered configuration. The dichroic filter will block as much as it can of the excitation light and just let the emission, the Raman scattered light go through. So if we're throwing in 10 to the 20th excitation photons, a good filter these days will cut out 8 orders of magnitude. So that will still be 10 to the 12th photons coming back. It's really hard to filter all the excitation light, but we can filter enough of it, and it's a different color than our Raman scattered light. So we can again go to our diffraction grating, spread out the light like a rainbow, take a picture of the rainbow. And then because the excitation light is so intense relative to our Raman signal, it's traditionally just chopped off on the plots because it would overwhelm the plots. So the laser line we set as 0. That's our 0 point, that's our starting point in energy. And then we plot a Raman shift. How much energy did we lose? And Raman shifts plotted in inverse centimeters, which is sort of a weird unit. It's usually referred to as wave numbers. I've yet to look up the historic reason why it's inverse centimeters. I suspect it was because it comes out as sort of convenient numbers to use, where not too many zeros, not too many decimal points. We can go from 50 wave numbers to 4,000 wave numbers and work in a nice range where the numbers aren't too unpleasant to work with. Anyway, so the laser line, which is the Raman scattering, no change in energy, no information that we're interested in this moment, is plotted at 0 and then just chopped off. Usually the diffraction grating is rotated in such a way that the excitation line is falling off the camera. And then we plot how many photons at each color we collected, and we plot it with this Raman shift, this shift in energy from the excitation line to where we detect the light. So the molecular vibration is encoded on this x-axis. Here is titanium oxide stretch. Here's silicon stretch. I happen to take this spectra, so I happen to know what these are. And then the intensity corresponds to how much of that molecule is there, but it also corresponds to what the laser power was, what the exposure time on the CCD camera was, the blaze under diffraction grading, the quantum efficiency of the detector, how well you were focused on your sample, this whole mishmash of convoluting issues. So in general, people don't worry about the intensity so much just because it's so variable just with the experimental setup, and people worry mainly just about this shift on the x-axis. And the nice part about vibrational spectroscopy now is that we're sensitive to the specific bonds, the specific arrangement of atoms. So if we have diamond and if we have graphite, they're both pure carbon. If you use some of the analytical techniques that just give you elemental analysis, it says they're both carbon. But because now we're looking at the bonds, the specific bonds have different strengths. We know, intuitively we know this, diamonds are hard, so those bonds are strong. The graphite is weak, it comes apart easily, it has different bonds, different physical properties, different electronic properties, different optical properties, all arise from the differences in the crystal structure. We can use Raman to distinguish the crystal structure. The diamond has a very clean peak at 1333 wave numbers, and it's just a nice single peak. The graphite has multiple peaks. Graphene has a different set of peaks, especially when you're down at single layer graphene. The ratio of the G and 2D bands are different. Carbon nanotubes have a different set of bands. So looking at the vibrational energy levels lets you see exactly the crystal structure and how they're oriented. It's quite sensitive to crystal structure. It's also quite sensitive to strain. If you have a material that's strained, that will shift how fast it can vibrate. You can think of it back on our balls on springs model. If you have the spring pre-stretched or pre-compressed and then try to have it vibrate freely, it's going to do that at a different frequency. And that different frequency will show up as a shift in the peak position on the x-axis. And then especially for 2D materials, and I'll show some examples in the last week, the strain can change the bandgap of the material. You can actually go from an indirect bandgap to a direct bandgap just by having strain on the material. And so this is all important things to worry about. And Raman is a really powerful way to probe whether you have strain on the material, what your crystal structure is, things like that. You can also do polarized Raman, which again gets at the crystal structure orientation, similar to the second harmonic generation orientation. But when you're doing spectroscopy, you don't get to pick, I want just this physical phenomenon, I want just that physical phenomenon. You throw lots of photons in, you often get everything happening at once. So the fluorescence or PL, if your light will couple into an electronic transition, you'll get a lot of fluorescence. Fluorescence is a much more efficient process than Raman. So you will your signal. Here I have the same sample. It happens to be Kevlar, which is a bulletproof vest material. And I ran it with two different lasers. I ran it with a green laser and a red laser. The green laser had enough energy to couple into an electronic transition, so we had lots of fluorescence. The red laser didn't have enough energy in each photon to couple into an electronic transition, so then we have very low fluorescence. So in Raman, you tend to have multiple laser lines on the same instrument, and that allows you to try to shift away from electronic resonances. You can either shift above the electronic resonance or below the electronic resonance, and that will start to decouple in spectroscopic space where the PL and the Raman show up. You can do mapping. So Raman is a point-by-point technique, but you can, of course, move your sample back and forth, back and forth, back and forth, and build up a picture, keeping track of your spatial positions when you take each measurement. So you can go from an optical image where maybe you can't really tell what's going on chemically to a beautiful chemical image. Here I've put cursors around the peak that corresponds to a silicon-silicon stretch, and cursors that around a peak that correspond to an aluminum oxide stretch. The metals don't have any Raman signal. So to have a Raman signal, you need a change in polarizability. Metals, the electrons are free to run around, so they don't have a change in polarizability. The electron cloud doesn't come back to where you started. And we'll go through selection rules next week. But that's just why the metal lines on this computer chip don't have any Raman signal. Metals don't have Raman signals. Metal oxides do. So this is an example that Bill Wilson brought me. He was looking at MOS2, that was CVD chrome. And of course, the question is, where are the single layers? Where are the bilayers? Where is there strain in the material? So for MOS2, there are two peaks that are looked at, and the distance between the two peaks spreads as you go from 1 layer, 2 layer, 3 layer, 4 layer, 5 layer. And so you can go from this optical image where if you squint, you can sort of make guesses, and certainly lots of groups sort of squint and guess whether it's a single layer or bilayer. Doing the Raman spectroscopy, you take a spectra from every single point. And if you look closely at all these spectra stacked on top of each other, you can see that there are some, like over here, the peaks have shifted up. Here, the peaks have shifted down. So you can take the distance between each of these points, and you can take the distance between each of these peaks and plot it out, and you can see where the single layers are, where the multi-layers are quite clearly. You can also do the PL map of this and then see where the strain is, because that will change the P. And just as one more example where you comparing Raman and photoluminescence. So the Raman peaks tend to be very narrow, sharp lines. They're nice, discrete vibrational energy levels. The PL ends up being bigger because these are the electronic energy levels. And within the electronic energy levels, there's multiple permitted vibrational energy levels. So if you're getting peaks and you're not sure what's going on, looking at the width of them will often help distinguish Raman from PL. That's not always perfectly true, but it certainly helps. The other thing to do is to shift laser lines. So remember that the Raman is a shift from the excitation line. So if we plot it in wave numbers, the Raman will always be in the same position. But if we plot it in nanometers, like I've plotted it here, the Raman will shift as you shift the laser line. So if I plotted the MOS2 excited with a 633 nanometer laser line, then the Raman peaks would shift down here and be right on top of the PL. By shifting to 532 nanometer laser, the Raman peaks shift up out of the spectral region where the PL is. All right, so Fourier transform infrared spectroscopy is the other vibrational energy, vibrational level technique. So where Raman was a scattering process, FTIR is an absorption process. You can think of it as very similar to the UV-VIS. The only exception is that now we're transitioning directly between two vibrational energy levels rather than transitioning between electronic energy levels. We have a slightly different geometry in the instrument just because for the spectral range that's in resonance with a lot of vibrational energy levels and molecules, we need to work from 3 microns to 20 microns, 3 microns to 50 microns, and some more modern instruments. And getting optics to work across, an order of magnitude of wavelength ranges is hard. And so people came up with this Fourier transform trick, which gets you away from having to use refractive optics and dispersive optics. Diffraction grating is dispersive, but usually diffraction gratings are blazed and designed for a certain wavelength, and it works for a couple hundred nanometers around that, but it doesn't work for, going from 3 microns to 20 microns. So inside an FTIR, we have a glow bar. A glow bar is our broadband infrared source. It's just a piece of silicon carbide that you run current through until it heats up. It's like a not very good Thomas Edison light bulb. It doesn't even produce visible light. But anyway, there's often a little reference laser that just gives you a guide beam. And then the light is sent through a beam splitter. So with the glow bar, we get all colors of light, all frequencies of light in the mid-infrared all at once. We send them to 2 mirrors with the beam splitter. One mirror just sits there, the other mirror is a scanning mirror, and it scans back and forth. As it scans back and forth, we'll get light going in and out of phase. So we'll get constructive interference, destructive interference, constructive interference, destructive interference. And so we're using the wave properties of light and the constructive and destructive interference of light. We then send these 2 beams through the sample, and the sample will absorb specific wavelengths of light, specific frequencies of light that corresponds to vibrational energy transitions. And we detect the light, and what we actually detect is this interferogram, this intensity of light as a function of time. And the function of time is related to the position of the scanning mirror. So we know how fast we're scanning the mirror. So at each time, we know where the scanning mirror is. So we can convert this time axis really into a scanning mirror position axis. Then we can do a mathematical transform called the Fourier transform. And that takes us from the time domain to the frequency domain. And we can plot here as a percentage of transmission which frequencies are strongly absorbed, which frequencies are missing in this interferogram after the light's interacted with the sample. And then we can interpret these missing peaks as molecular composition of the sample. So that's how FTIR is often used for chemical analysis. In my lab for quantum materials, I often see it as just people using it to measure the bandgap of materials, where the materials have bandgaps in the near or mid-infrared region. And there's different modes that you can run FTIR in. Most instruments have all these modes available. So you can run in transmission. You just run your light all the way through. In the past, people used to get up sample window has sort of fade with time because it's a lot of prep work. Especially if you're doing 2D materials, if you're exfoliating 2D flakes, you can have a double polished silicon wafer. As I mentioned, silicon is transparent in the infrared. So if you have a double polished silicon wafer, you can exfoliate flakes right onto that, and then the silicon will be transparent in the infrared. So you can see what is the absorption of your 2D flake that you've doped and tried to design something to work. Tune the bandgap in the infrared region. A lot of samples, a lot of FTIR systems have this ATR technique, which is a attenuated total reflection. Here we bring a crystal into contact with the sample. It can be diamond, it can be silicon, it can be germanium, something that's transparent in the infrared. We couple the light in such that it totally internally reflects at the interface between the crystal and the sample. And just an evanescent electric field penetrates into the sample. So some people claim it's surface specific. The evanescent electric field penetrates about 500 nanometers into the sample. On a lot of samples I work with, 500 nanometers is enormous. So you can debate how surface specific it is. It's half a micron, it's not particularly surface specific. at least in my world. It does require having this optical coupling between the crystal and your sample, and you have to physically contact the crystal to the sample. So it tends to be fairly unpopular for quantum materials. People just don't want to touch something to their sample. You can also do it in reflection mode. So just shine the light down, look at which frequencies are reflected. If the sample strongly absorbs a specific frequency, that frequency won't be in the reflected beam. You do often end up with sort of fringing interference between the reflections off the sample and the reflections off the substrate. But if you just understand what those are and expect to have some interference, fringing effects that are just periodic, these two beams coming in and out of phase relative to each other, you can interpret it. But for the quantum materials that have come through my lab, most people are just doing FTIR and transmission, looking again on that absorption onset where the band gap is as they try to tune the material's band gap. Just some other notes about FTIR. You can plot FTIR on two different y-axes. You can plot it as %T or %R or as absorbance. You can do this also in UV-VIS. %T and %R, if you're trying to just measure the optical band gap or something like that, %T or %R is usually fine. Absorbance is used more if you're trying to do chemical analysis. You know, do I have a methyl group attached to this thing that I've designed? In general, they look very similar. %T or %R, your signal is going to be dips relative to a baseline of 100. And absorbance, your signal is going to be peaks relative to a baseline of 0. The one thing to really pay attention to is the % transmittance is a linear scale, and the absorbance is a log scale. The log scale, the peaks, the absorbance scale, means that how high your peaks are is directly related to your concentration. In the linear scale, it ends up being exponentially related. How deep your dip is exponentially related to your concentration. So if you're trying to interpret how much of a certain chemical group you have there, if you're functionalizing, you're adding new chemical groups, and you want to characterize how many you have there, then you want to plot in absorbance, because then you can just look, sample A has a peak twice as high as sample B, so sample A was the better functionalization procedure. You'll see data plotted both ways, % transmittance and as absorbance in the data. And it's important to sort of understand what the different implications are as you plot the data in different ways. So just why the %T and absorbance are like that. So absorbance of light by a sample goes as the Beer's law or Beer's-Lambert law. The %T is your intensity with your sample in place over the intensity with no sample. And it goes as E to the minus epsilon LC. Epsilon is the molecular absorptivity. It's a fundamental how probable it is for the molecule in your sample to absorb a photon. So it's just fundamental to your sample. L is the path length. How much sample does the light interact with? And C is the concentration. If you plot in absorbance units, you take the negative natural log of I over I naught, and that gets rid of that exponential, and then it's just epsilon LC. So epsilon is again a fundamental parameter of your sample. L is the path length, so assuming that you make your samples so they all have the same volume of sample that's interacting with light, then the absorbance is linearly related to the concentration. So by plotting in absorbance, FTIR becomes semi-quantitative, whereas Raman, it's really hard to do semi-quantitative Raman because there's so many variables that can play into the intensity of your spectra. Often you want to do a baseline correction. In Raman, you do a baseline correction to subtract off the fluorescence and look at just the Raman peaks. In FTIR, you do a baseline correction to account for light that was scattered out of the collection optics. So the instrument assumes any light that didn't make it to the detector must have been absorbed by the sample, which is not perfectly true. It could be reflected by the sample, it could be scattered by the sample. There are things where the light doesn't end up going exactly along the collection path. And that usually has a very weak wavelength dependence. So the entire spectra is offset or sometimes sloped a little bit. And so you can fit a baseline and just subtract it off to get rid of the scattering and look at just the absorption of your sample. And one thing to be extra cautious of when you're doing FTIR is atmosphere. So as I sit here and talk, I spew out water vapor, I spew out carbon dioxide. Carbon dioxide is the one that trips people up more than water vapor. But so carbon dioxide is this set of peaks here. There's two really nice peaks right around 350 wave numbers. So if I take my baseline, I start taking measurements, and then my friend comes in and I start talking to my friend, the carbon dioxide levels will go up and I'll get two nice peaks here that look really nice and people want to interpret them. Alternatively, if I'm talking to my friend and then my friend leaves and the carbon dioxide level goes down, you'll sometimes get these negative peaks. And then people will come and ask me, why do I have negative peaks? That makes no sense. Well, you were breathing near the sample or you were talking to somebody and then you quit, and that lowered the concentration of carbon dioxide in the area, and it shows up in the measurement. The water vapor is a bunch of little narrow spikes up here and over here. The little narrow spikes tend not to trip people up. They look more like noise and people are less inclined to interpret them. You get a bunch of little spikes because the water vapor ends up in different clusters. There's a cluster of 3 water molecules and a cluster of 11 water molecules, and that will change the vibrational resonance. And so that's why you get these multiple peaks out of the water vapor as water sticks to each other in a variety of different ways. So just be really careful around peaks around 2350. Usually in FTIR software, there's a atmospheric compensation algorithm. Like, these are well-known peaks to people who do spectroscopy and people who make the instruments. So you can usually go into the data processing menus and find atmospheric compensation, and it will correct for the water vapor and carbon dioxide. So the blue data was the raw data in this example, and the red data had this post-processing data processing step applied to it. You can still see there's a little glitch around the carbon dioxide. There's a little glitch in the red data, but it's not as noticeable as the blue data. But something to be extra aware of if you end up trying to do FTIR on samples. But FTIR is diffraction limited. So as we said, the diffraction limit is half the wavelength of light. We're trying to use light that's like 20 microns, so we can focus down to about 10 microns with infrared light. 10 microns is really big compared to a lot of 2D materials and quantum materials. Often people bring 2D flakes that are 3 microns, 4 microns across. So those would all be, you wouldn't be able to focus on just the flake. You'd always have some of the substrate. Raman does nicely. It gets down to about 300 nanometers, which is often good enough, but it's still fairly large compared to some of the materials that people want to work with. So one trick is to use scattering scanning near field optical microscopy. So here we have an atomically sharp metal tip, and we focus the light onto it, and we use it as a little lightning rod. So we're localizing the electric field by using this curved metal tip, and then we can localized down to the electric field interaction with the sample down to basically the curvature of the tip, which people will quote 10 nanometers. Realistically, it's probably more like 20, 25 nanometers. It depends how sharp your tip is and how careful it is and things like that. But then you can actually get much more localized light sample interactions by using this intermediate metal tip to moderate the interaction. So then you can see things like plasmons. So plasmons, anything that ends with an on in physics is a particle. So it's an oscillation of the electron density in the sample with respect to the positive ions in your sample. So here is a schematic of a scanning near field optical microscope. We have an interferometer, very similar to the FTIR. We use a quantum cascade laser rather than a glow bar. So the quantum cascade lasers are much, much brighter than the glow bar, but they have a much narrower spectral range. So you have to pick a quantum cascade laser that happens to be in resonance with what you're looking for. So they have, I don't know, 300 wave number range, 200 wave number range, and trying to build up a full spectral range with a quantum cascade laser ends up being prohibitively expensive. So they end up being, these systems end up being designed for a very specific set of measurements. You then have the metal coated AFM tip, and you have it come close to your sample, and you excite an electric field in it with the laser light. And then you can start imaging these plasmons as they propagate around your sample and reflect off interfaces and things like that. So in conclusion, there are lots of ways for light to interact with matter, and really trying to understand how the light interacts with matter is important when you're trying to make a measurement. If you just treat the scientific instrument as a magical black box and you push the button and it spits out data and you take the data and try to publish it, you're not doing science. It's not making any sense. You need to actually understand what's going on inside the instrument to be able to interpret the data that it puts out. All right, and with that, thank you for your attention. This is a topic that I tend to be excited about and tend to ramble a long time about. So thank you for your attention, and I'm happy to have any questions. All right, is there anything in the chat? Nope. All right, questions, anybody? No, no questions. All right, well, I'll wrap it up then. Next week, we'll talking more about sort of the mathematics and selection rules and exactly why different techniques work on sort of a more mathematical physics basis rather than the more practical how instruments are put together. And then the final week, we'll do a bunch of examples of quantum materials and measurements that are made, and hopefully everything can be synthesized together in understanding of what these papers are talking about for the measurements they made. All right.